So just a quick recap of what we covered so far on data preprocessing. If you've noticed, I uploaded another file for data preprocessing part 2, which I'm going to start today. But before that, I want to finish part 1, and I'm using that slide right now. So we talked about the definition of data preprocessing, and that is basically whatever you do actually to your raw data, just to prepare it for the analysis. Like, for example, let's say you collect a data online, or you start from like a publicly available data set. Most real world data sets are not ready for analysis. They are messy, they have duplicates, they have typos, they have inconsistencies, they have missing values, and a lot of other problems, like the data set may be too large. And so it's good to do some data preprocessing, which also affects the quality of your analysis. So the main reason we do it is to improve data quality. And we also talked about dirty data and different types of problem with the data, like incomplete data, or for example, if the data are not in the right format, we do the transformation. If we are dealing with a huge data set, like millions of rows or thousands of features, maybe we want to do data reduction. And we are going to talk about them more in detail today. So these are the 4 main steps of data preprocessing, like data cleaning, reduction, transformation, integration. So do we need all these process for each data set that we are working with? Yes, actually, no, we don't need all of these. It depends. It depends on the data set. So if, for example, if you have, for example, maybe your data set, for example, is not too large, you don't need to do data reduction. You only need, for example, data cleaning to handle, for example, missing values or duplicates. Maybe your data comes from one source, then you don't need data integration, or maybe it comes from multiple sources, then you need also to do the integration, right? Or maybe it has several issues coming from multiple, which is the most of the time in the real case scenario, right? Data comes from different places. All of them are messy, so you need data cleaning, integration, and also we are living in big data era. Data are huge, and so for all these reasons, sometimes you also need all of that, sometimes not. And then we talked about data cleaning. We talked about missing values, incorrect values, inconsistent values, noisy data, and so on. And what are the ways to deal with them? So, for instance, for data integration, and so before moving into each of them completely, we provided an overview of each one. So after data cleaning, we talked about data integration, and that if data comes from different places, then we want to combine them first before doing any analysis. And one of the most common problem here is that when the sources are different, there might be some inconsistencies, and we have entity identification problem, which is basically is just to make sure how can we, for example, make sure that the records or the data that we get from different databases are referring to the same thing. For example, if it's about people's ID, let's say a student ID. So in a previous session, I mentioned we may store a student ID in one database as a student ID, somewhere else as a student number. It doesn't mean that they are different. They are still referring to the same thing. There are just some inconsistencies in terms of like the name. Or other problems, like, for example, different, data type, the format, like you use dates in different formats, in different data sets, and so on. And then we talked about data transformation, that is transforming data in the form that is ready for analysis. What does that mean? So we said that sometimes we have, for example, you have the example I mentioned about agent salary. If you recall, I mentioned the ranges might be very different, right? So you have salaries from 0 to, I don't know, $1 million, and then you have age from 0 to 100. So if you don't scale them, if you don't normalize them, then depending on the algorithm that you are going to use, most machine learning algorithm will dominate the or favor the attribute with higher values as more important, which is actually not right. So the big numbers dominating the model, but in reality, you don't want that, right? It doesn't mean that salary is a more important feature compared to age. Another thing that we discussed was example of, for example, two customers buying the same amount, like spending the same amount of money. Let's say you have a business, you have two customers spending the same amount of money. One of them is spending $200, but only made two purchases, each $100. The other one spent the exact same amount, like $200, but purchase more number of items, let's say 20 items, each like $5 or $10. And so do we treat like these two as a business? Do we treat these two customers the same, or should we provide the same recommendation to them? No, we often don't do that. They have two different purchase patterns, and so it's good to sometimes create, for example, or construct new features. So this first point here referred to what I just mentioned, creating new features from the given ones. For example, average sale amount instead of total sale amount, and so on. And then finally, discretization, which I'm going to explain probably next lecture on Wednesday, which is transforming numeric attribute into symbolic ones or categorical features. Then we talked about data reduction. So we just talked about why sometimes smaller data is even better than a large data. So many of like our data sets are just too big to handle. They may have, for example, too many rows, too many columns, and it doesn't necessarily mean that we need all of them, right? So maybe you don't need, I mentioned, for example, the data from Twitter, if you recall. I had access to many features, like maybe hundreds of features, but did I really needed all that features for my analysis? So depending on the type of analysis, depending on your question, your business question or your research question, depending on that, you may need different features. Can you provide some examples here? Example of when, for example, you have more, for example, features and you use just subset of your features, or you have a very large data set and you use a subset of like the rows.
Shoot. Yeah. Maybe like when you have like a large data set of like chess games and you only want to train on a smaller amount because it's like too many games to train with.
Yeah. So what features, for example, you select?
Like, yeah, there might be like a lot of I don't know. They might have like a lot of. This is data reduction, not like feature, not like reduction of features, but that would be like data reduction. So like, you don't take the entire set; you take like a smaller subset.
Yeah. So if you, for example, we have different ways to do the data reduction. You can go across the columns and select subset of columns or subset of features, or you can just select subset of rows using, for example, sampling techniques and so on, or even reducing like the values, like value reduction that I'm discussing now. So for instance, I'm going to provide more examples later, but for now, let's say you have this data. And so we talked about feature reduction, case reduction, value reduction. So the first one is just focusing on the features, that is the number of columns. Let's say you have, back to the Twitter example I mentioned, let's say I had hundreds of features for the tweets. Like, for example, number of likes, number of shares, number of retweets, length of the tweets, and so on, and so many other features, users information, and so on. So I may not need all those features for example, measuring, for example, the speed of the tweet, right? I may not need that. Or for example, if you're analyzing, for example, users' sentiment, what do you need? Do you need all that information? No, you only need, for example, to access users' comments. And so sometimes you need a subset of features, not all those features. And that's feature reduction, reducing the number of columns. And case reduction is reducing number of rows. So sometimes you say, okay, I have 1 million of rows, but do I need like that 1 million or 10 millions of rows of customers for my analysis? Maybe even a subset of that. For example, let's say 100K or only 10K customers. If you sample properly, may be representative enough. And then it will lead to much faster data analysis. And finally, we also talked about value reduction, reducing the number of distinct values. Like, for example, if you have age, instead of having ages like 10, 20, 21, 22, 23, let's have 0, for example, to 10 years old, 10 to 20, 21 to 30, 31 to 40, and so on. Or, for example, you have a column for salary or income. Instead of listing like all the different values, like, for example, 100K, 101, 110, 200, and so on. We just put like ranges, right? 100 to 150, 150, for example, to 200, and so on. And then we moved further into like each one of like these stages. For example, in data cleaning, we talked about missing values that can be represented in different ways depending on the data that you have. For instance, if you're working with Pandas data frame, and in case you don't know what Pandas is, Pandas is just a library. It's a very useful library in Python, which we often use for data analytics. And so this is an example of a data frame, which is very similar to SQL tables. It has rows and columns. So this is a sample of a Pandas data frame or table showing data from a very famous Titanic data set. So I'm not sure if you have ever heard of Titanic data set, but this is a very famous publicly available data set. Even if you just Google it, you can find it. You can find several analyses related to this data set. It's commonly used in machine learning, data mining, and data analytics courses. So as you can see, we have several features here, which are the columns of the data frame, like these are all your features. And we also have a class label, which is survived. So for example, if we want to see if a passenger survived or not, this would be our class label, right? And these are the features that we use for prediction. Now we have also some missing values. Can you identify them? I actually accidentally hit enter, and so you can see the missing values. So these are the missing values represented with NaN. So because I was using Pandas data frame, you see NaN. In SQL, they can be null. If, for example, you're working with CSV file, they might be, for example, with empty string and so on. So in any case, all of them representing missing values in your data. And we have to deal with them. So in this example, which columns include missing values? Cabin and age, right? Now, if you look at the data carefully, you see that the cabin column has a lot of like this is just like the preview of the data, not the whole data set, right? But even looking at the first 7 rows of the passengers, you can see that the cabin information is missing for most passengers. And you can get, for example, later I'll show you in our hands-on session, I'll show you how to get, for example, total number of nans in each column and so on, or in total. So you see which columns or which features have the most missing values. So most of the time, if, for example, especially if that column is not very relevant for your analysis, you can use feature reduction, right? So you can just get rid of that column or columns or features that include lots of missing values or are not relevant for your analysis. That's one way to like handle missing values. Or you can just remove all the rows. So you can see removing the tuple containing missing values usually done when the class label is missing. So now another way, which is also very common when you have non-values, is that people just get rid of all the rows containing missing values. But what is the problem with that? What is the problem with removing all the rows containing missing values? When do you think we can use it? And when do you think it is better to avoid that? Anyone wants to answer that question? Okay, let me check the chat. So I think it depends on what proportion of rows are removed as well. Yep, exactly. And so if, for example, let's say, if you have lots of missing values spread out like in different, for example, rows. So, for example, here, look at this. If you want to get rid of the rows containing null values, then you are getting rid of like most of the rows, right? And it doesn't make sense because you're losing lots of information. It makes sense if, for example, you have missing values in your class label, right? So if your class label, let's say, survived, include missing values, and then you get rid of those rows, that makes perfect sense. Why is that? So let's say, for example, we had nan here. Can you see my mouse?
Yeah.
Okay, so let's say you have missing values here, 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 right? Does it make sense to get rid of the rows including missing values if those missing values are in the column survived?
Yeah, I think that's pretty important.
Yeah, because they are not informative, right? So because the whole, for example, let's say goal of your analysis, if it is like seeing which features can better, for example, predict whether a person survived or not, and if you don't know whether the person survived or not, and if that information is missing, for example, if you don't know if Miss Lina was survived or not, so it doesn't matter even if you have all the other information about this, right? So if the missing value is in your class label, then it makes sense, for example, to get rid of that record. And because of that, just useless for your training. But if you have many rows with missing values and you have lots of attributes, then it's very dangerous because then you are losing a lot of information. And another way to handle missing values. So I didn't mention filling the missing values manually because this is like in most cases, especially for large data sets, this is just not feasible. Do we have any question? What types of rows are removed? Data is missing for certain demographics, maybe. So if you remove those rows, we have four. So I'm going to show this here so everyone can see. If missing values doesn't affect the analysis or conclusion, then we can get rid of them. Yeah, so it really depends on the data, on our analysis, and you have to, there isn't like a right formula. You have to check what makes sense in each scenario. And filling with the missing values manually doesn't just make sense most of the time, especially for large data sets, because it's very time consuming and maybe also prone to error. Removing the tuples containing missing values, which I already explained, or filling it with global constant such as 0, unknown, infinity, or anything that makes sense in that context. Now, let's see some smarter strategies, which I also explained last session, which was replacing null values with mean or median, or for example, even a smarter one with a local estimation. And let's see what each one of these means. So replacing missing values with mean or median, this is common. And if depending on the distribution of your data, so always in your analysis, before doing any data analytics, before applying any algorithm or model, please start pre-processing and data cleaning and deal with these things before moving on to the next step. And one of the best thing you can do is to check the distribution of your data. So if it has a normal distribution, it doesn't matter if it is like mean or median, right? Because then mean and median for normal distribution is almost the same. So in that case, you can fill with either. But if you have a skewed distribution, it's better to fill it with median. And recall my example from previous session when I was talking about, for example, salaries in a company. And I said, let's imagine you're working in a company with, I don't know, 200 employees. And most employees, let's say 190 employees, have salaries less than 100K or less than 150K. Whereas only few employees are earning more than 500K. This may shift your average or your mean towards a higher number, for example, 250, 300K, but it is not a good estimator for the income of an average employee, right? Because most employees' income is less than 150K or less than 100K. And if that's the case, median is a better representative because median means median care about the frequency, right? So it represents how many, for example, people are having, for example, what is the most, for example, common income? If it is like, for example, 100K or 120. So that would be more representative in this case. Now, so if your data is normal distribution, either is fine. If it's skewed, use median. Another smarter strategy. So if you're going to go with this one and you want to fill in here, what you should do, finding mean or median of the income, right? And then replace this missing value with that. For example, if the distribution is normal, replace it with mean, otherwise replace it with median. Now, what about local estimation? Now, local estimation says, okay, instead of using one mean or median, global mean or median, let's use the mean or median within the same class. So what is your class label here in this table? Credit. Yep. So now we have good people with good credit and bad credit. So what this method is offering is that instead of putting, for example, replacing this missing value with mean or median of the income for all customers or all employees, let's replace it with only the ones that have bad credit, because this person apparently is classified as bad credit. And so let's only focus on the customers who had bad credit, like this one and this one. And then, as you see, their income is much lower, right? And then replace it with the mean or median of those data, right? Those data points, not all. Now, this is even better because it's more, because people in the same class tend to be more similar. Like people with bad credit tend to have, for example, less income. And another even more accurate method is replacing the missing value with the most probable value. So we let the model just predict the missing value. Not the model could be KNN, decision tree, regression, right? So whatever model, just for example, if in this case, if the person which is 35 years old and is male and whose credit is bad, instead of replacing it with mean or mean and median of the class, of this specific class, instead of that, you just let the model predict what income is most likely. And this is the most accurate one, but it's also more expensive to compute. And then we talked about noisy data, where actually the session ended. So I'm going to explain more about this today. What was an example of noisy data? For instance, you have temperature data, 20, 21, 21, 22, 21, and then 100 degrees. So that 100 is your noise. Now, what does this noise come from? Several places. It could be due to faulty data collection instrument. For example, maybe your sensors are malfunctioning, and that's why you see 100 degrees. Maybe it's because of data entry problems. Maybe because, for example, there was only a typo. or maybe there was data transmission issues. And so because noises they don't follow the overall behavior or trend of data, and they don't represent any pattern or behavior, they are just errors, and that's why they are just random errors or variance in the measured data. They do not measure any. They do not have any meaningful. They do not lead to any meaningful results, right? So if we don't handle them, then our model will learn the noise instead of the pattern. Now, what are the ways we can handle noisy data? We can do binning, clustering, regression, moving average, and so on. And I'm going to explain them today. So with binning, we group by nearby values into bins and then replacing them with some representative value. That representative value can be mean or boundaries and so on. And I'm going to explain it in a few minutes with an example. So, for example, and this is why binning helps, because for example, when you do binning, we said that we smooth by bith means or median or boundaries, etc. So when you're smoothing the data, it means your extreme values or the random fluctuations or noises that you have, they are getting averaged out. And so they show the overall trend instead of just getting the noises. And for example, if you have, for example, daily temperature, if you check the, for example, weather data, daily temperature or hourly temperature may fluctuate a lot. But then if you see the weekly, for example, average, then you can see a better, clear pattern. And then clustering is just, again, we group the data that are more similar and closer together into one cluster. And values that don't fit into any group, they are just outliers. And regression, just a smoothing by fitting the data into regression function. Now, that function can be a line, can be just a smooth line or curve. The goal is that we just fit the points into that to see the overall trend. And it just helps to capture what is your main trend. And we also ignore the noises there. And then I'm going also to explain moving average. This can be better explained by the example. So I'm just quickly explaining what it does, and then we see it with example. So moving average in this method, each of your values or data points are replaced by the average of its neighbors. For example, the stock prices, they fluctuate a lot. But if you get 7-day, for example, moving average, it shows a better direction. And so it just cancel out the random fluctuations and make the overall trend more consistent. And that can be better explained by a diagram. And then finally, combined computer and human inspection. So in this one, algorithm flag the values that are suspicious, and then humans decide what to do. And the reason that it is important is because some of our outliers are errors and others are rare but are important. That means not all the noises are errors, not all of them. Some of them may be, for example, if you have a sudden spike in sale, okay, this could be because of a data error, but it could be also mean successful marketing campaign. So sometimes we care about them. Now, this is important, and you probably have this type of question in your midterm exam. Binning, for example, question. We have two types of binning, equal with equal depth, the types that I'm covering today. So equal with, so in general, binning, in the binning, regardless of the type, you have to first sort your data, and your data is always numeric for binning. So you first sort the data and then group them into several bins, and then you just replace the values that are inside each bin with some other values that are more representative. For example, replacing all values in every bin with the mean or median of that bin. And this just reduces the noise because then individual values are getting pulled toward a more common value. And so our goal here is we just want to reduce the fluctuations that we have or noises by grouping the nearby values together. Now we are explaining, I'm going to explain these two types, equal width and equal depth. So in equal width partitioning or equal width binning, we divide the range of attributes into n intervals of equal size. What does that mean? So you divide the range of values into n bins that have equal size, and I'm going to explain this with an example better. So you have to first see what is your lowest and highest value in the numbers that, for example, I give you several numbers, you sort them, you find the highest and lowest. Let's say B is the highest value, A is the lowest value. And then I ask you, for example, that I want you to group them into 3 intervals. So I also give you the number of bins or intervals, which is, for example, 3. And then using this formula, you can find the width or range of each bin. Now, each bin in this method will have the same width. And this is the most important thing here. And so you, if I think I have example here. Yes. So if you see the data here, I already sorted the data. So if they are not sorted in the exam, make sure you have to sort data first, find minimum and maximum. So for example, I ask you partition this into, for example, using equal width binning into 3 intervals of the equal size. So what do? You first, and let me use the marker here. You have to find the width first, right? And as I said, width is equal to your largest number. This is your B, right? 34 minus your smallest number. So this is max minus mean, 34 minus 5 divided by 3, because we want 3 intervals of equal size. Now this gives you 29 by 3, which is 9 point something, about around 9.6. Now, as I said, I ask you to partition into 3 bins, and your task is to find out what are the which values go into each bin, right? So how do we identify that? First, you find this number, which is the width. Now, each bin should have the equal width. What does that mean? So you start with 5, and then you have 5 plus 9.6. This gives you the range of this bin. So this bin goes from 5 to 14.6. Now looking at the data points, which number go into this bin? Hello, wake up.
It should be 5, 8, 9. They're
Yes,
less than
8
14.
and 9. Yeah, exactly. So 5, 8, and 9, because they are less than 14.6. How about 15? No, because this is not in this range, right? Now we go to the next one. Now I'm going to the next one. Now 14, so we start from where we left, right? So the range of the previous one closed at 14.6. So we start here. Then we again add the same width, right? Because the range or the width should be the same. The model is equal width binning. So the width, this is the same. So plus 9.6, right? This gives you
24.2.
24.3, right? If these numbers are not correct, you can correct them, but they should be approximately correct. So which numbers here in your data points fall into this range? So we already put 5, 8, and 9 in bin 1. Next number is 15. Next is 21. Next is 21. And next is 24, right? Next is 25. Can we include 25 here? No, because this is not in this range, right? So bin 2 is 15, 21, 21, 24. Now we go to the next bin. So here we have the next bin. Now we start from 24.3, right? And then we add 24.3, we add 9.6, and the result would be 33 something, right? Let's say until 34, because our last number is 34 and this is our last bin, right? And so you include the rest of the numbers in this bin. Now the reason, so one important thing here is that the width, these bins are equal width, they have the same width. And the other thing or question is that do we have the same number of values in each bin in the equal width binning? No, we don't have. We don't have the same number of values. For example, in bin 1, you see that in bin 1 we have 5, 8, 9. Bin 2 we have 4 values, and bin 3 we have 5 values. So the number of values in each bin, they are not the same, but they have the same width, where width is this number, gives you like this range, right, for each bin. Now, after we do this, so the next step is smoothing by bin means. So back to previous slide, if you see the definition here, I mentioned that we divide the range of attributes into n intervals of equal size. You find width with this formula, and then as you see here, we can use, for example, a smoothing by bin means or by bin median or boundaries and so on. So let's use means, for example. It means that you replace all these 3 values with the mean of bin 1, which is 7. Then replacing all values in bin 2 with the mean value of bin 2, and replacing all values in bin 3 with mean value for bin 3, which is 28. And the other method is smoothing by bin boundaries. If you want to smooth by bin boundaries, it means that you have to replace each value with the nearest boundary. So what is the boundary? Boundary of each bin is the minimum or maximum of the bin. For example, bin 1, what are the boundaries? 5 and 9, right? Bin 2, what are the boundaries? 15 and 24. Bin 3, what are the boundaries? 25, 25, and 34. So the mean and max of each bin, those are the boundaries of the bin. Now, if you want to smooth by bin boundaries, it means that you have to replace each value with the nearest boundary. So what is the nearest boundary to 5? 5 itself, right? This is the boundary itself. What is the closest or nearest boundary to 8? Is it 5 or 9? It is closer to 9. And then 9 is also replaced by 9. Now we go to bin 2. Again, we want to smooth by bin boundaries. What are the boundaries? 15 and 24. For each value, you check which one is closer. For example, 15 is closer to 15. 21 is closer to 15 or 24. It's closer to 24. So 21 is replaced by 24 because it's closer to 24. And again, 24, the same, is replaced by 24 because it's closer to 24. Now, who can explain the same thing with bin 3?
The middle 3 values are closer to 25 because
Yeah.
there's not much difference between them. 26 is close to 25. Same thing with 28. 28 is closer to 25 as compared to 34.
Yep, exactly. So you just for each value, you look at the boundaries and select the one that is closer to that value. For example, here, these values are closer to this one, so they are getting replaced by 25, and 34 is your maximum, right? Now, this is about equal with binning method. And I'm going to remove this.
Professor, I have a doubt with bin 3. In the last iteration, I think you rounded off the value of the range to 34, right? We were getting 33.8 something, right?
24.3. What would have been the number? The exact number?
1 second, I just
Point
flipped it.
two. You said 0.3, but it's 0.2. I don't think it makes a big difference.
Yeah, the exact number is 24.267. And if we add 9.6 to it, we get 33.867, right? So, I mean, is it okay to approximate it to 34?
Yeah, because that's the only last number remaining, right?
Okay, but I mean,
And we
shouldn't it
have 3
be
bins.
okay? I mean, it's okay to add that number in the bin 3, right?
Yeah, yeah.
Because in the case of bin 1, I think the range was 14.6 something, right? And we
Yeah,
still added 15 to the next
bin
bin,
one,
right?
let me calculate. Just give me a second to
Sure.
okay, bin 1 will be because your bin width is now 9.67.
Yeah.
That's the exact number, 9.67. Then
Yes.
your bin 1 will be 5 to 14.67. Your bin 2 will be 14.67 until 24.34, which includes also 24, right? And then bin 3 would start from 24.34 until some numbers which is actually your last bin. Even if it's like 33 something, then it just doesn't make sense to add another bin for example, only one 34 number, right? For one value.
Oh yeah, now it's working. Yeah, got it.
So equal with binning, just grouping your values by their numerical range. It doesn't group them by the count of values. So when I'm explaining equal depth now, you will see that in each bin in equal depth, you will have same number of values, but in equal width, we don't actually care about that. We only group them by numeric range or the width. And then we can smooth them by either means, median, or boundaries, which I already explained. So now equal depth binning method. So if I go back here, you see equal depth as the second method of the binning. Divide the range into n intervals, each containing approximately the same number of values. And why do we say approximately? If you're dividing the range into already n intervals, like let's say we have 12 data points, and I ask you, I want 3 intervals. So you know that we have four values in each, right? So if you have 12 data points and you want to have 3 intervals or 3 bins, it means that each bin contains 12 divided by 3, which is 4 values, right? So in what cases it can have approximately the same number of values?
When it is indivisible by the
Yeah, when you have, for example, odd number of values, data points. What if you had 13 data points? So 13 data points, and I ask you like 3 bins, then one bin should have like 5 values instead of 4, and that's okay. You can have like 5, 4, 4, or 4, 5, 4, 5, 4, and so on. But the most common one is 5, 4, 4. So the first one, you include that in the first one. So now let's see an example of equal depth binning. In equal depth binning, here again, we have the same data points, 12 data points, and we want 3 bins. And in the exam, don't worry about how to find, for example, the number of bins, because I already asked you that. So each bin should contain the same number of values. So for example, if bin 1 has 4 values, it means that all other bins have almost the same number of values. And so we had 12 data points with 3 bins. It means that the first 4 values going to bin 1, the second 4 values going to bin 2, and the last 4 values going to bin 3. And if we had odd number of data points, like for example 13 data points instead of 12, then it would have been 5, 8, 9, 15, 21, then 21, 24, 25, and so on. So 25, 26, and so on. So in that case, you started with 5 numbers and then 4 and then 4, if you had 13 data points. And again, the rest is the same. Smoothing by bin means it means that you replace each value with the mean of that bin. Mean of bin 1 is 9, so all values are replaced by 9. Mean of bin 2 is 23, all values are replaced by 23. And mean of bin 3 is 29, so all values are replaced by 29. Now, smoothing by bin boundaries, again, the same thing. So you replace each value with the bin boundaries. What are bin boundaries? Mean and max of that bin. So mean and max of bin 1 are 5 and 15. Other values are replaced with the one that is nearest to them. For example, second value was 8, which is closer to 5, so it is replaced by 5. 9 is also closer to 5 compared to 15, so it is replaced by 5. Now we go to bin 2. Now in bin 2, 21 and 25 are our like mean and max, or our boundaries. And the middle values like 21 is getting replaced by 21 because it's closer to 21, right? It's actually the same. And 24 is closer to 25, so it is replaced by 25. And the same process for bin 3. They, for example, all these 3 values are getting replaced by 26 because they're closer to 26. Now, do you have any question about binning? So let me go back if you have any question here.
I do have one question, Professor.
Yeah.
So for the bin means we are calculating the approximate value of the mean of the bins, right?
For the bin means,
Yeah.
we replace each value with the mean of that bin.
So the mean of the first bin is I think 9.25.
Yeah.
So we are approximating it to 9.
Yes.
Or okay. So for example, if in the first bin the numbers are 5, 6, 7, 8, then the bin mean is 7.5. So in that case, what should we write
I would,
for the
if for the exam, I will let you know the instructions. So like whether you have to, like for example, round up the numbers at all, like, or leave them as like real numbers instead of, for example, integers. So for simplicity here, I just use the integer numbers. And if that's the case, then I'll let you know that always, for example, round up.
Okay, thank you so much.
No worries. And then we have regression, which is, as I said, fitting a smooth function to noisy data, so that you can understand what is not actually fitting it to the exact noise or outlier. I didn't mean that. Fitting that actually into your data points, to just understanding the relationships and being able to make the predictions. So each blue dot here, so all these blue dots here, representing your data points, right? So these are your data points. And this line is y equal to x plus 1. So this is representing x plus 1 function. This is because when x is 0, then your y is 1. And if it was x minus 1, then the line was this, and so on. So this is the line that fit this data the best, or representing our like the pattern of that our data. And we don't try to pass through every point, right? We don't like do this to passing through every point. We just try to capture the overall trend of the data or overall pattern of the data. And then if we have some points that are very far from other points, like for example, this one, if we have points like this, these are representing what? Everyone? Outlier, right? So these points are just representing outlier. They don't follow behavior. and the general behavior of the data. We have two types of regression that we covered so far: single linear regression, multiple linear regression. And so single linear regression simply means that you have one input, one output. Like, for example, you want to predict salary based on years of experience. So if that's the case, then this is a single linear regression. But what if you want to predict salary not only based on years of experience, but also more features like years of experience, gender, level of education, and so on? And then in that case, it will be multiple linear regression. So if you have multiple input, one output, then it will be multiple linear regression. Now, cluster analysis. So clustering, we just group the data points that are similar to each other without using labels. So this is unsupervised learning, as I mentioned before. And each data point here again is your each blue point here is your data point. And these points that are closer together, as you see, for example, these points formed one cluster, these formed another cluster, and this is another cluster. And then we always often have some points that don't fit into any cluster. They are far from any of like these clusters, and they just represent our outliers. Now, these like plus signs here, they just represent the cluster centroid, which we discuss them later when we go into details of cluster analysis and how to calculate them, which is out of the scope of this session. Now, what do we use cluster analysis for? Many use cases like social network analysis, any unsupervised form of data where you don't actually want to predict any class label, or you don't know even what you want to predict. You just want to group data and do some analysis and find some patterns or behaviors, finding communities, customer segmentation, or for example, you just want to find abnormal behavior and so on. So it just helps you to find out those structural patterns that you don't know their categories in advance. And so this is the last one, moving average. And so moving average smooth noise data by replacing each value with the average of its neighbors. And so instead of you trust only one, for example, noisy measurement, you can check the nearby values and then average them, replacing that with the average. I can explain it better with the example. Don't worry. But in general, you are typically using it for time series data. And the reason is because time has order. You have, for example, yesterday, today, tomorrow, right? There is an order in time. And so we can often use this moving average for based on the neighboring values, because they are also related to each other. And so the length, or L, which is here, length is just the number of neighboring points that we use. So L is just showing how many neighbors you want to use. If you use, can you tell me which higher or a smaller L result in more smoothing? So higher L, what does it mean? Higher window length, what does that mean? L is number of neighbor points that you use, that you average. If you use more number of neighbors, it means that more neighbors from which you take the average. Exactly. And then it means that you are more smoothing the data. But it may also hide the some trends in your data. So for example, let's see this last example here. Now here, what is our window size, or our L? It's 3. It means that we are using 3 data points for finding like this moving average number. Now we have 3 columns here: year representing year, sales, and then moving average. So instead of having like these individual sale numbers for each year, we can use moving average. So for instance, what is the moving average for year 1994? It's null. here is null because we need previous value, we need current value, and we need the next value. So for each year, we need previous value. For example, let's say year 1995, we need previous value, which is 2. We need current value, which is 5. And we need next value or next year value, which is 2, right? So the average would be 3, and we replace this with 3.
Does the window size have to be an odd number? In this case, it's an odd number. But if it's an even number, how would that work?
What would be your window size? Would be an even number?
Yeah, can it be an even number?
So you want to, for example, get, for example, for year 1996, getting 2 previous years and 1 next year. Doesn't matter. You can do that.
Okay. See.
Then you can do, for example, for 1990, again, for 1995 will be null because then you don't have 2 previous values. But for 1996 would be the average of 5222, right?
Yeah, so an odd number would slightly, an even number would slightly be skewed either to the back or to the front.
So the more number of neighbors that you use, doesn't matter if it's even or odd. The more numbers that you use, it means that you are more and more smoothing your data. But it is also dangerous because it may mean that you're too smoothing, that you don't get the pattern of your data. So here, this one is null because we have no previous value. Then 1995, we average 252. That is the previous value, the current value, and the next value, which is 3. Then for 1996, we do the same. It means that we average the previous value, the current value, and the next value, which is again 3. Then for 1997, we do average of 227, which is 3.67. 1998 is the average of 276, which is 5. And then for 1999, again, it's null because we don't have the next year value. Now, if you look at this diagram, you can see that this line shows, for example, sales, and this line shows years. So x-axis shows year, and the y-axis shows sales. Now, the yellow trend is for related to your original data based on sales. Whereas if you use moving average, you see this red one, this red line, which is smoother, right? So you smooth out the data. It doesn't like have all these noises, but you have to also be careful with not smoothing it too much. Now, it's already almost 5:10, and I'm going to quickly going to the next slides. But before that, let's do a quick Zoom poll. This is a very quick question. So there's a question in the chat box. For moving average, do you do previous, current, next divided by 3? Yeah, because we were taking the average, right? Because there are 3 years that we are considering. If we were considering, let's say, 4 or 5 neighbors, then we had to divide by 4 or 5, depending on the numbers, because we are getting the average. So the average is not, you have to divide by the total numbers, right? Can you see the question?
Yeah. Yes.
Okay, great. Okay, great. 80% participated, 88%, 91%. Come on, 9 more percent. Okay, so I'm going to end poll. What is the main goal of data preprocessing? Share results. So the main goal of data preprocessing is all of the above. And most of you answered correctly: to improve model interpretability, to reduce noise and errors, to make data suitable for analysis. So all of them are correct. Can you see the second question? No, today I won't use iClicker because I already recorded your participation using the Zoom. So I can, using the Zoom, I can see who were the participants. You can have more than one correct answer. You can select more than one correct answer. Okay, now end the poll. So the correct answers are the first and second one, handling missing values and removing duplicate rows. And it's because normalization is not a data cleaning technique. It's one of the data pre-processing technique, right? But it's data transformation and not data cleaning. Sampling also is not data cleaning. It's just also data reduction technique. And so stop sharing this and share results with you. So what is the question for moving average? We do like instead of 3 numbers, we choose 4. For example, we're on the list. Would it be 94, 5, 6, 7 for average, or would there ever be a case where instead of 94, it would be 98? Here, you are using your you want to smooth out the noise, right? And you want to try to use the average of the neighbors. So if you are using the, I don't see the rationale behind using the data that are further apart rather than the closest neighbors. So we often, especially with like time series data, you often use the closer neighbor because then they might share more like similarities. And but you can use L larger or smaller. If you use a smaller L, just means that you are less doing smoothing. And if you use larger L, like 4 or 5, then it means that you're, for example, this line will be even smoother. Now, let's share these slides. Okay, I'm going to skip the recap. In case you don't know, these are the slides from data. I think the name of the file is Data Preprocessing Part 2. You can find it on eClass. So on eClass, there are 2 files for data preprocessing, Part 1 and Part 2. So I'm skipping the review parts because we already explained everything in detail today and also in previous lecture. Now, this is today's outline. Mainly next lecture's outline, but I'm providing an introduction today. So data reduction techniques that we covered so far were feature reduction, case reduction, or value reduction. And you see some new names here, and I intentionally use these names in case that you have any questions. Or for example, if you see these names somewhere else, you know what they are the same. So dimensionality reduction is the same as feature reduction. So we keep all the rows, but we delete some columns. So the focus here is on the features. For example, back to the Twitter example, you have maybe a lot of information or features about the tweets, but you may need only a few of them for your analysis. Or for example, you have a lot of information about your customers, but you only need, for example, customers, I don't know, age and gender or some other demographic information for a specific type of analysis. You may need, for example, for predicting salary, you may only need, for example, years of experience, education, gender, and so maybe a couple of other attributes, whereas your real data may include, for example, 50 attributes, right? So that is if you select subset of your features and remove the rest, that is you keep all the rows but delete some columns, this is what dimensionality reduction or feature reduction means. Now, numerosity reduction focus on the number of data points. So this is exactly the same as case reduction. So they are the same thing, just different names. So case reduction or numerosity reduction is the opposite of the dimensionality reduction. In this case, you keep all the columns or keep all the features, but you take fewer rows. Recall my example when I said, imagine you have data with, for example, 10 millions of rows, but you only take, for example, these are your customer data, 10 millions of customers. And then you only select a subset of rows, like 10,000 of them, instead of 1 million or 10 million, right? And that is case reduction. So you keep all the columns, but you select the subset of your rows. Then we have value reduction. just means that you keep the same table, but you just simplify the values. For example, instead of, if you're, for example, you have salaries like 100K, 110, 120, 130, you don't keep them as they are, because you have many different values for example, salaries instead. And they may not be, for example, for what you are going to measure, depending on your analysis. Maybe that like salary feature, all those different values are not like, there aren't a meaningful difference, for example, between salary of 100K with for example 110. You know what I mean? So for example, maybe you can provide a range of salaries, for example 50 to 70K, 70 to 100K, 100 to 150. For example, let's say in a banking system, you want to decide whether you want to mortgage a person or not, and you don't you may not consider their salaries like all individual salaries. For example, someone's salary is 119K, the other one is 120, the other one is 121. They are almost in the same range, right? So you may only consider 100 to 120, 120 to 150, and so on. And so this is another type of data reduction. And finally, we have data compression, where we reduce the storage size of the data. And there are two types of data reduction that I'm going to cover next lecture, which are PCA, principal component analysis, and LDA, which is linear discriminant analysis. There are, of course, other methods, and I'm going to briefly explain them, but the main focus is on PCA and LDA. Now, the whole idea is that, let's say, for example, you have a data set about people, persons, and you have some information about them, like their height, weight, their shoe size, their, for example, leg length, and so on. These are maybe, for example, patients' information. And many of these information or columns are related to each other. And what dimensionality reduction do is actually trying to reduce these number of features into fewer number of features, which still capture the same information. So for example, let's say you have height and weight. So instead of individually considering height and weight separately, you combine them together into one new feature, call it, I don't know, total body size, something like that, and use that only one feature. And in principal component analysis, you call that new feature as your principal components. Now, here is your iClicker question 1, which I prepared for an in-person class. But because today's class is on Zoom, I actually put this in the Zoom. Just give me a second. I'm going to share this with you now. You should be able to see this question. And I'm going to finish the class at 5:30. So those of you, if you have class, you can leave and watch the recording. But 70% responded so far. So the question asks, you have a data set with 1 million rows and 200 features. You randomly select subset of the rows, that is, for example, 50K instead of 1 million rows, but keeping all the features or all the columns. What type of data reduction is this? Now, this is clearly dimensionality reduction. Sorry, this is clearly numerosity reduction or case reduction, because you are selecting subset of the rows, right? You keep all the features, you keep all the columns, and you are reducing the number of rows, so it's numerosity reduction or case reduction. In what case it could have been dimensionality reduction? So for example, in the same data set, if you kept 1 million rows, so you kept all the rows, and instead of 200 features, you only, for example, chose, I don't know, 20 features, right? In that case, that was an example of dimensionality reduction. Or you could do value reduction, which I explained, data compression, and so on. And this is the result, just in case you want to see it. And I'm going to stop sharing that too. So I'm going to provide just a brief introduction of PCA because I already provided this introduction in my first class too. And I want to make sure that both sections are at the same page. So PCA, or principal component analysis, is just statistical method that is often we use in data analysis as a dimension as a data reduction technique, and it just find the direction where your points are most spread out. So the main important point here is the variance, and so the main question that actually the PCA is going to answer is how can I summarize my data set? How can I summarize this data in fewer dimensions? How can I reduce the number of dimensions? So back to the example I mentioned, I said, suppose, for example, you have data set with several features of persons like height, weight, leg size, and shoe size, and so on, right? Now, let's say you focus on the two features of height and weight. And these two, considering that these two are highly correlated, for example, people that are taller people tend to also weight more. If that's the case, then using PCA, or principal component analysis, we can create a new feature combining height and weight. So instead of using them separately, we combine them and we get something like, for example, overall body size, right? And now this new feature is your principal component. And if you have like 100 correlated features, your PCA may compress them into 10 components and is still keeping most of the information. How? So you have several principal components, PC1, PC2, and so on. So PC1 is a direction where your data has the most variation or the highest variance. And highest variance means it is capturing maximum amount of variability in the data or the most amount of information. So PC1, highest variance and also highest amount of information. PC2, the next highest variance or next principal component with most information, and so on. So you reach to the point where you see that you don't need to include all the data, but you can only, for example, keep PC1, PC2, like just these first few principal components. And so the most important thing is to know what principal component is. They are just these new variables, for example, total body size, that are constructed as linear combination of initial variables, where your initial variables could be weight and height, right? Instead of using weight and height, you create a new variable based on linear combination of these two. And another important thing is that these are linearly uncorrelated variables. It is the ones that you created. So height and weight are related, but the principal components that you create, for example, total body size and other features that you are creating, they are linearly uncorrelated because you already combined all the related ones together. And so here is just the process that you first have to normalize your data and scale the data. Of course, for example, if you have features like income and age, then income or salary will dominate age if you don't normalize your data. And then you have to find your principal components or the new directions in the data or the new axis. So that is why you have to compute the orthonormal vectors or principal components. So the first axis is just explaining what is the most variation, and the second one just showing the next most, and so on. And this is just to better represent this. So as you can see, originally, like, our data points have two coordinates, x and y. But what this picture is showing, this is your principal components or the variations of each principal component. So this is the PC1 with the highest amount of variation and highest amount of possible information. Second PC or PC2 is the second most variation, capture the second most variation, and also a second most informative one, and so on. So in general, PCA try to put the maximum possible information in PC1, then maximum remaining information in PC2, and so on. And also this one has the largest variance, then this has the next largest variance, and so on. And so if you think of, for example, about height and weight again, height and weight example, now this line is representing the overall body size. So we reduce two features into one without losing much information. And the height of each bar here is just showing how much variance. You should see that this is percentage of explained variance. This is how much variance each component has. And the black line is just connecting like these bars to show what is the overall trend. And we just want to see, we use this, for example, type of picture images to decide how many components we want to keep. And yeah, that's it for today. I'm going to further explain PCA and LDA next session. Let's see also this question before we leave. What statement best describes what PCA does? So this is the last one. Sorry for taking longer than expected. Okay, 54 participants responded so far, 60%, 70%. Okay, I'm going to end the poll. Most of you answered correctly. The correct answer is option B, PCA find directions that capture the maximum variance in the data, as I mentioned. It just want to find directions that capture the maximum variance or where the most informative part or most information is. And PCA remove all redundant features but keep the original ones. No, it is not. It's not about removing like any redundant feature. We are just creating new features based on the existing ones. And the last one is also not correct. PCA always improve classification accuracy. We don't even care about class labels in PCA. So it doesn't do anything without that. It may improve classification, but it is not intentional. So it doesn't guarantee that. And okay, this is also the results. Do you have any question? Let me stop sharing my screen and see if you have any question. No more questions? So just one more thing.
Hello?
Yep.
What exactly is data compression again?
Sorry?
Data compression? Like, what exactly is data compression?
You can think of it like a zip folder. You just keep your table as it is. You don't change anything. You don't remove features. You don't remove values. You just compress the size of your data. So you're just reducing the size of the data. Like when, for example, you store your data in a zip folder. Okay. Do we have more questions? Jean-Lin, did I answer your question? You mentioned for my previous question, for the example, L3 and for 1996 interval can you please unmute your mic if you still have this question and let me know because it is not clear what you wrote here.
Hello. Are you able to hear me?
Yeah.
Is it fine if I share my screen to show you?
Yeah.
I sent a share request. I think you have to accept.
Sorry, just give me a second. You should be able. It's like multiple participants can share.
Oh, yeah.
Yeah, it shows that you started the screen sharing.
Like for 1996, when it was L equals 3, we looked at like the intervals for the moving average to calculate the moving average. We looked at 1995 and 1997 along with 1996 when it's L equals 3.
Mm-hmm.
But if the L equals 4, would we look at the year 1994 or 1990 or 1998?
For which year? Like, for example,
like
you always look
yeah.
at your neighbors. Like, for example, 1996, if you want to consider the like previous 2 years plus the next year, then it will be like 1994, 1995, 1996, 1997.
Oh, okay.
Yeah. Do you have more questions?
No.
Otherwise, I can finish the class. Just one more point. Your midterm exam will most probably be on the week before the reading week. Sorry, so I think your reading week should be on the week of February, I think 14, something like that. So, and I guess 1 week before your reading week is a good time for the midterm exam, depending on how much we can progress until that time. And your quiz 1 will also be before your reading week. So we decided to keep only 2 quizzes, 2 online quizzes, one before the reading week, one after the reading week. So one, let's say, closer to the midterm time, and the second quiz closer to the final exam time. Is that okay?
Yes, Professor.
Okay, sounds good. And I'll continue this lecture on Wednesday. Try to finish, ideally, finish this on Wednesday lecture, and then next Monday we can have a hands-on session on data preprocessing. Okay, if you have no more questions, I can then end the Zoom meeting. Okay, have a good day. Bye-bye. Bye.
Bye.